Hello, curious minds. Welcome back to ProjexCellence ProDigy, your one-stop solution for all your project management and mechanical engineering needs. I'm Govind, a certified PMP and mechanical engineering professional with more than 25 years of experience in the power and energy sector. In our ongoing series on project management knowledge areas, in lesson 1, we learned about project integration management, the glue that holds everything together. In lesson 2, we discussed project scope management, doing the right work and only the right work. And today, we move to the lesson 3, project schedule management. And the theme for today's lesson is simple, practical, and extremely important. Time is money. Just think about for a moment. Suppose if a project is completed late, in that case, labor cost will go up, equipment remains occupied longer, and penalties may apply. Customers become unhappy and business opportunities may be lost. On the other hand, when a project is completed on time, it means resources are utilized efficiently, stakeholders remain satisfied, and the organization achieves its objectives as planned. That is why managing the project schedule is one of the most critical responsibilities of a project manager. In this lesson, we will understand what project schedule management is, why it is important, and the 6 processes that help us plan, develop, monitor, and control the project schedule. So let's get started. Why project schedule management is so important? In every project, time is one of the most valuable resources. Once time is lost, we can never get it back. Imagine you are carrying out a project which is major overhauling of a power plant engine. The moment the engine is shut down, the power plant stops generating electricity from that unit. So in this case, every additional day of delay means lost revenue for the plant owner, which means every extra day costs money. Delays can increase labor cost, equipment rental cost, accommodation cost, and project overheads. In some cases, they may even result in contractual penalties. The second reason why the schedule management is so important, because there are always resource limitations. In any project, we have a limited number of manpower, tools, equipment, and budget. If suppose one activity takes longer than planned, those resources remain occupied and may not be available for other activities. This can create a chain reaction of delays throughout the project. The third reason is customer expectations. Customer always wants project to be completed on time. Delays can lead to dissatisfaction, damage business relationships, and sometimes even cause the loss of future opportunities. So what is the purpose of project schedule management? The primary goal is to ensure that the project is completed on time. It helps us plan activities, arrange them in the correct sequence, allocate resources effectively, monitor progress, and take corrective actions whenever necessary. What is project schedule management? PMI identifies 6 processes in project schedule management. And these processes are the journey from creating a schedule to ensuring the project finishes on time. First process is plan schedule management. Before creating the project schedule, we must decide how the schedule will be managed. In this process, we establish the rules, procedures, and guidelines for schedule planning, development, monitoring, and control. In simple words, this process creates the roadmap for managing the project schedule. Second process is define activities. Once the project scope and WBS are ready, we identify the specific activities which are required to complete the project. Normally, work packages in the WBS are very large pieces of work. Here, in this process, we break them down into smaller and manageable activities. Third process is sequence activities. After identifying the activities, we determine their logical order. Not every activity can start immediately. Some activities depend on the completion of others. This process establishes relationships and dependencies among activities. Fourth process is estimate activity durations. Now we know the activities and their sequence. So here in this process, we estimate how long each activity will take. And these estimates are based on resource availability, experience, expert judgment, and historical data. This process answers the question, how much time will each activity require? Fifth process is develop schedule. This is where everything comes together. We combine the activities, their sequence, duration estimates, resource availability, and project constraints to create the project schedule. And the result comes in the form of a Gantt chart, network diagram, milestone chart, or schedule baseline. This process helps us to plan the start and finish dates of project activities. Sixth process is control schedule. Once the project execution begins, the schedule must be continuously monitored and controlled. We compare actual progress against planned progress. If delays occur, we analyze their causes and take corrective actions. These actions could be fast tracking, crashing, reallocating resources, or revising the schedule. The objective is to keep the project aligned with the approved schedule baseline. Types of dependencies. Dependency simply means that one activity has a relationship with another activity. According to PMI, there are four types of dependencies: finish to start, start to start, finish to finish, start to finish. And the most common is finish to start, FS. In a finish to start relationship, the successor activity cannot start until the predecessor activity is finished. For example, in a solar power plant project, we cannot start installing solar panels until the mounting structure have been installed. Similarly, in an engine overhauling project, we cannot start assembling the engine component until the inspection and repair work has been completed. So one activity must finish before the next activity can start. That is why it is called finish to start. Second is start to start relationship, SS. In this relationship, the successor activity cannot start until the predecessor activity has started. Imagine you need to lay a 1 kilometer long underground power cable. So for this project, the first activity would be trench excavation, where workers dig a trench along the cable route. And the second activity is cable laying, where the cable is placed inside the trench. Now here is one question. Do we need to wait until the entire 1 kilometer trench is excavated before starting cable laying? The answer is no. As soon as the excavation team completes the first 100 or 200 meters, the cable laying team can begin laying cables in that completed section. So here in this case, excavation starts on day first, and cable laying cannot start before excavation starts. But cable laying does not need to wait until excavation is fully completed. Both activities can run simultaneously after excavation has begun. So this is called a start to start relationship, because the cable laying activity can start only after the trench excavation activity has started. The third relationship is finish to finish, FF. In this relationship, the successor activity cannot finish until the predecessor activity has finished. Here, the activities may start at different times, but their completion is linked. Imagine developers are writing code while another team is reviewing it. The reviewers can start reviewing early, but they cannot complete the entire review until the developers finish writing all the code. Since the completion of the review depends on the completion of coding, this relationship is called finish to finish dependency. The fourth is start to finish. This is the least common dependency type. In a start to finish relationship, the successor activity cannot finish until the predecessor activity has started. For example, suppose a company is migrating its application from an old server to a new cloud server. So here we have two activities. Activity A is start new cloud server operations, so which we call predecessor. And the activity B is stop old server operations, which is successor. The company cannot shut down the old server until the new server has started operating successfully. So here the old server keeps running. The new cloud server is configured and tested. And once the new server starts serving users, the old server can be shut down. So the finish of the old server operation depends on the start of the new server operation. This is called start to finish relationship. PMI also classifies dependencies based on where they come from. And these dependencies can be mandatory, discretionary, external, and internal. Mandatory dependencies are those that are required by the nature of the work. In simple words, we have no choice. The work itself dictates the sequence. For example, in an engine overhauling project, we must dismantle the engine before inspecting its components. These activities must occur in a specific order because of technical or physical requirements. That is why they are called mandatory dependencies. They are also known as hard logic. Discretionary dependencies. These are based on best practices, experience, or the preferred way of doing work. Unlike mandatory dependencies, these can be changed if needed. For example, in a software development project, a team may prefer to complete all coding before starting testing. However, if the project is behind schedule, testing can begin on completed modules while coding continues on the remaining modules. The dependency exists because of preference, not necessity. Therefore, it is a discretionary dependency. These are also called soft logic or preferred logic. External dependencies. External dependencies are those that depend on external parties or vendors or event outside the project team's control. For example, waiting for government permits, customer approvals, or regulatory clearances before proceeding with certain work. Internal dependency. Internal dependencies exist within the project and are under the control of the project team. For example, in a software development project, user acceptance testing cannot begin until system testing has been completed. Both activities are managed by the project team itself. Similarly, in an engine overhauling project, component assembly cannot begin until inspection and repairs are completed. Since both activities are within the project's control, so this is an internal dependency. Next topic is estimation techniques. Once we know the activities and their sequence, the next question is how long will each activity take? PMI provides several techniques to estimate the activity durations, like expert judgment. In this technique, we use the knowledge and the experience of experts who have performed similar work before. For example, suppose you are constructing a house and need to estimate how long it will take to build the brick walls. An experienced site engineer who has supervised dozens of similar house construction projects can easily tell you that based on his experience, constructing the walls will take approximately 12 days. Since this estimate is based on the engineer's knowledge and experience, so we call it expert judgment. Second technique is analogous estimating. Analogous estimating means using the duration of a previous similar project as a reference. For example, suppose last year your company completed a 20 megawatt solar power plant project in 120 days. Now you are planning another similar 20 megawatt solar project under similar conditions. So you can easily estimate this project will also take approximately 120 days. Since we are comparing with a similar past project, so this is called analogous estimating. Third technique is parametric estimating. This technique uses a measurable unit and historical productivity rates. The simple formula is duration is equal to quantity divided by productivity rate. Suppose a team can lay 100 meters of cable per day. And if the project requires 1000 meters of cable, then simply to calculate the duration will be 1000 divided by 100. So 10 days. So therefore, the activity duration is estimated as 10 days. Another technique is 3-point estimating. This technique considers uncertainty by using 3 estimates. Optimistic O, best case scenario. Most likely M, normal expected scenario. And pessimistic P is worst case scenario. For example, suppose software development is estimated as optimistic 8 days and most likely 12 days and pessimistic is 20 days. So PMI commonly use the PERT formula to calculate the estimate. E is equal to O plus 4M plus P whole divided by 6. So if you calculate this, so it will come 12.67 days, approximately 13 days. Next technique is bottom-up estimating. This is generally the most accurate technique. Instead of estimating the whole activity at once, we break it into smaller tasks and estimate each task individually. Then we add all estimates together. For example, suppose in an engine overhauling project, engine dismantling takes 2 days. Inspection of components takes 1 day. And repair takes 3 days. Components assembly takes 2 days. And engine testing take 1 day. So total duration will be 2 plus 1 plus 3 plus 2 plus 1 is equal to 9 days. Here we estimate each component separately and then combine them. So this is called bottom-up estimating. Next process in project schedule management is develop schedule. Now that we have identified the activities, arrange them in the correct sequence and estimated their durations. So the next step is to develop the schedule. This is where all the schedule planning information comes together. In this process, we combine the list of project activities, activity dependencies, duration estimates, resource availability, and project constraints and assumptions. Using all this information, we create a realistic project schedule. The schedule may be presented in the form of Gantt chart, network diagram, or milestone chart. Once the schedule is reviewed and approved, it becomes the schedule baseline. During project execution, we continuously compare actual progress against this baseline to determine whether the project is ahead of schedule, on schedule, or behind schedule. Any changes to the schedule baseline must go through the project's change control process. Now let's discuss one of the most important responsibilities of a project manager during project execution, which is monitoring schedule performance. Creating a schedule is only half the job. Once a project work begins, we need to continuously check whether the project is progressing according to the approved schedule baseline. This process is known as schedule control. And the objective is very simple. track progress, identify delays early, and take corrective actions before small delays become major problems. PMI recommends several tools to monitor schedule performance as milestone tracking. Milestones are significant points in the project. For example, foundation completed, equipment delivered, installation completed, testing completed, project commissioned. So project managers regularly compare planned milestone dates with actual milestone dates. Another tool is schedule variance, SV. Schedule variance measures whether the project is ahead of schedule or behind schedule. And the formula for this, SV is equal to earned value EV minus planned value PV. If the result is positive side, so it means the project is ahead of schedule. And if SB is 0, it means project is on schedule. And if SB value is negative, it means project is behind schedule. For example, suppose by today the project was planned to complete the work of worth $100,000. However, only $80,000 worth of work has actually been completed. Then in that case, SV will be 80,000 minus 100,000, which is negative 20,000. So negative schedule variance indicates the project is behind schedule. Another important metric is the Schedule Performance Index, SPI. It tells us how efficiently the project is progressing compared to the schedule. And the formula is SPI is equal to EV earned value divided by PV planned value. If SPI is 1, so it means project is exactly on schedule. And if SPI is greater than 1, it means project is ahead of schedule. And if SPI is lesser than 1, so it means project is behind schedule. For example, suppose earned value EV is $80,000 and planned value is $100,000. So SPI will be 80,000 divided by 100,000 and the result will be 0.8, which is less than 1. It means project is behind schedule. In other words, for every day planned, only 80% of the expected work is being completed. So all these tools help the project managers keep projects on track and ensure timely completion. Now let's go through another important concept in project schedule management, which is critical path method, commonly known as CPM. Critical path method is a schedule analysis technique which is used to identify the longest sequence of dependent activities in a project network. Although we call it the longest path, it actually determines the shortest possible time in which the entire project can be completed. At first, this may sound confusing, so let me explain. Imagine your project has several different paths from the start to the finish. Some paths may take 10 days, some may take 15 days, and one path may take 20 days. The project cannot finish until every path is completed. Therefore, the path that takes the longest time determines the overall project duration. And that longest path is called the critical path. And the activities fall in critical path are called critical activities because they have zero float, also known as zero slack. Zero float means there is no flexibility. The activity with zero float cannot be delayed even by 1 day without affecting the project's completion date. Now, let's discuss a situation that every project manager eventually faces. Imagine your customer says the project must be completed 2 weeks earlier than planned. Or perhaps the project has already been delayed due to bad weather, material shortages, or technical issues. At this point, the project manager has one challenge. How can we finish the project sooner without reducing the project scope? This is where schedule compression comes into play. Schedule compression is a technique which is used to shorten the project duration without reducing the project scope or quality. In other words, we still deliver everything that was originally agreed upon, but we try to complete the work in less time. PMI describes two common schedule compression techniques, crashing and fast tracking. In crashing, we add extra resources to complete an activity faster. And these additional resources may include more workers, more engineers, additional equipment, extra work shifts, or overtime. The objective is to reduce activity duration. For example, suppose you are overhauling a large power plant engine. Normally, one team carries out the entire overhaul and the job takes about 25 days to complete. However, due to some unexpected problems, the project falls behind schedule. To recover this lost time, the project manager decides to assign two teams instead of one. So one team works in the morning shift while the second team works in the afternoon shift. So by using additional manpower and extending the working hours, the overhaul is completed in 24 days, which is one day earlier than the original schedule. So this is called crashing because we have shortened the project schedule by adding extra resources without reducing the project scope. So the biggest advantage of crashing is that it helps reduce the project duration and allow the project to be completed sooner. However, it also has some disadvantages. Since we are adding extra resources, so the project cost usually increases. Also, there could be another problem. If the additional workers or teams are not managed properly, it can lead to confusion, poor coordination, and lower productivity instead of improving performance. The second schedule compression technique is fast tracking. Fast tracking means performing activities at the same time that were originally planned to be done one after another. Unlike crashing, we do not add extra resources here. Instead, we overlap the activities to save time. For example, suppose in a software project, the original plan is to complete all the coding first and then start testing. However, the project falls behind schedule. To save time, the project manager decides not to wait for the entire application to be completed. As soon as the developers finish one module, such as the login module, the testing team immediately starts testing it, while the developers continue coding the remaining modules, such as the payment module and shopping cart module. Here, coding and testing are happening at the same time. So this is called fast tracking. The biggest advantage of fast tracking is that it reduces the overall project duration without adding extra people or resources. Since some activities are performed in parallel, the project can be completed earlier. However, fast tracking also has a major disadvantage. It increases project risk. Let's continue with the same example. Suppose the testers have already finished testing the login module. Later, while developing the payment module, the developers realize that the user authentication process needs to be changed. Since the login module also uses the same authentication process, so the developers must modify the login module as well. Now, in this case, the testing team has to test the login module all over again. And this repeated work is called rework. So, although fast tracking helps save time, it also increases the chance of rework and mistakes. That is why project managers should use fast tracking only after carefully evaluating the risk involved. That brings us to the end of lesson 3, project schedule management. In today's lesson, we learned that project schedule management is all about ensuring that the project is completed on time. In our next lesson, we will explore project cost management, where we will learn how to estimate project cost, determine the project budget, and control cost throughout the project life cycle. If you found this video helpful, please like, share and subscribe to ProjexCellence ProDigy. Namaste, goodbye, Sampai Jumpa.